So recall that OWASP, this organisation, is just some group of people who have come together to try and promote the improvement of security of web applications. And one thing they do is list what they consider the top 10 risks in terms of web applications. We started with a couple of simple examples last lecture, first demonstrating cookies. And then we got to an example of a redirection. We'll not do it again, but just to remind you that we had one where the first one we looked at was with cookies. If someone can steal the cookie, then they can steal the session of another user. So if we can intercept packets between client and server, then someone can take the session information. Then we looked at a redirection attack which involved someone following a link, in our case, that took advantage of the feature of the website. The feature was a redirection. So let's just recap on that redirection. And we'll go direct to one of the slides. It's actually the last risk, the 10th one in this list, this unvalidated redirects and forwards. So the example is some websites have a page which will redirect you from that current page to some other URL. So an example is this URL on some website, redirect.php, takes as a parameter some URL, some domain or some complete URL, and when someone visits that, the code inside here takes the user and sends them to this location. So that's a feature that some websites implement. Why? One thing you'll see is sometimes the redirect may show a message before you actually are redirected. So a message you'll see is if you click on a link from some organisation's website and the link is to an external website, then the message say, in 5 seconds you're going to be redirected to an external website and we take no responsibility for this external content. So that's one example where you see this redirection used, that the website is sent, it has a link to some external one. Another form of redirection, or is forwarding. Sometimes websites implement some functionality such that to pass between different pages in the same website, to forward between pages, they also use some code to implement that. So an example that this website has this index.php which takes a parameter forward, FWD, and that points to another page on this website, say to the admin page. So sometimes that's used rather than absolute links, then a parameterized forward is used. So that's common in some websites. These attacks take advantage of those features. Okay, so if a website has a redirect or a forward feature, then attacks can try and take advantage of that by constructing URLs that redirect to some other website, some malicious website, or forward to some page which you should not have access to, and still using the trusted domain that the user who's accessing this website would trust. And that's what we saw in the attack. We saw a combination of phishing where we had this email. I received this email and it contains some URL and some message. So this is a combination of several issues, saying a fake email from someone who I normally would trust, so I think the email's okay. I check, there's a link in here, and some people know when there's a link in an email, should you trust it? Well, one way to check do you trust it is to look, right, if you don't know anything about the details of the URL, at least check the domain. is this domain something that I know about? So in this case, the idea from the attacker is that when I read this email, if I check the domain at least, www.myuni.edu, I trust that domain because I know that that's our uni grading system. So I trust this link and I click on the link. But of course, as I click on that link, if we look at the details, it's actually using the redirect feature of that website to take me not to the MyUni, but to some other malicious website. And that redirects me to that malicious website, which does whatever it needs to do to perform the attack. In our case, the malicious website provided a fake login page and collected usernames and passwords. But it doesn't have to do that. The malicious website may be just some website that gets money from people visiting it. So they have many ads on there. You are redirected to here, and therefore they get some money from the fact that someone else has visited this website. Or the malicious website may have some virus on it. So you're redirected to it, and then that virus infects your computer. So what happens when you redirect it, there may be different results. This took advantage of the fact that the reader of the email trusts the domain. What if you got a different email? What if the email was this? Well, maybe in this case, some readers would notice that it's not the real domain. Some may not. So here's a domain which is not myuni.edu, but it's similar. So maybe in a phishing attack, the reader of the email would be fooled in following this link. But maybe they're smart enough to realise, this is not really my website, I'm not going to trust this link. Okay? Or maybe if you receive this email, well, again, I think this case, the reader of the email may be even less trustworthy in terms of the link. That is, I see this, I don't recognise anything here that's familiar to me. I don't recognise the domain that I trust. Therefore, place less trust in this link. Maybe recognise this is a phishing attack. So this is about the idea that users are starting to place some trust in particular domains that they've visited on a regular basis. Or maybe this one. Okay, I receive an email and it says, takes me to some other website, which I have no idea about the domain name. I've never seen it before. It doesn't make sense to me. Therefore, as the reader, I may more likely to not trust and follow this link. Okay. Therefore, from the attacker's perspective, being able to construct a URL that contains a domain which is trusted by the reader is more likely to be successful in an attack. That's the point here. Questions?
How about if use a text that creates the original domain, but the link of that text is in different URL?
In this, okay, so in these examples, I'm including the actual URL in the email. Of course, you know, with some emails, you can construct emails with HTML where something is displayed here, but the actual URL behind that link is different. So with a HTML email, this is not a HTML email, it's just plain text. With a HTML-based email, you could construct a link that looks like a trustworthy domain, but is not. If you hover over the link, you'd see down here that it's not the domain. So, yes, that's another way of fooling the user into thinking that they trust this. But that's not about this attack. This attack is about the redirection. It's if the user does look for the domain, even if they look for the domain, with this redirection attack, we can still take advantage of that as the attacker. Because even if I'm the reader and I trust myuni.edu, so I check this, looks okay. With the other emails, I would not trust them. I recognise this is not my website, I'm not going to follow the link, This is just some IP address. I have no idea where this takes me. I'm not going to follow the link. This one, some other website. I know that's not my grading system for my university, so I won't follow the link. But with this one, I recognise at least, this is the website, the domain I always visit to enter grades, therefore I'll trust the link. That's the idea here. Now, there are other ways to fool users into following links. This is just taking advantage of this redirect capability. Now, this is just one example of using the redirect, of using emails. In some cases, it doesn't have to be that. That is, what if there was software that was checking the domains? That is, the security of the system was set up such that if there's a link in an email, and if it's to a trusted domain, allow that link. Let's say the organisation, SIT, has set up their email server so that any email that has a link in it, if the link is to a domain that is trusted, maybe on some whitelist, then we will allow that email, or we will allow that link in the email. That is, the SIT email server will not filter that. But if it's set up such that if the link in an email is to some untrusted domain, one that's not on a trusted list or a whitelist, then block the email or maybe strip out the URL from the email so that the reader doesn't check and follow the link. So if it was automated so that software was checking, only display links and only allow users to click on links that are to trusted domains, then if that was the case, this link would not be displayed because it's not trusted by the SIT system. The trusted ones are those that the SIT system knows about. This one would not be displayed, but that software would display this one, assuming that this domain, myuni.edu, is trusted by the organisation. So if we have some software to check the links and allow links to a set of trusted domains and block links to a set of untrusted domains, if that was the case, this would get around that, in that the attacker could construct this link, it would be accepted by this software because it's to a trusted domain, but in fact it turns out it redirects the user to some untrusted domain. So it's not just about emails. This redirection is another way to get around the fact that the user or some software does not know where they're ending up. So how do you stop it? Don't use redirects or forwards in your website. There's one solution. Okay? Avoid them as much as possible. If they are used, then the values that are supplied, make sure that they're valid or appropriate for the user that it's accessing it. In our example, it took a URL as a parameter, but you could place some restrictions so that the page checks, is the person visiting this website allowed to be visiting this? Especially for forwarding. For example, the forwarding, although I don't have an example, is we use this feature that it takes someone to another page in the website. In this example, it takes the user to the admin page to administrate some feature on the website. Well, that should only be available to some users that are logged in. So this page should check. If someone types in this forward to another admin page, it should check whether they're authorised to do that. Another way is to have the code, the application, to maintain some mapping. Instead of having a URL or an absolute link here, that we, in the URL here, we include some, say, random value that maps back to the actual page URL. In that way, the attacker cannot guess how to construct this URL. So make it difficult for the attacker to construct a URL to redirect to their site, because the application actually constructs the URL using their own internal mapping that the attacker cannot see. So that in this complete URL, we would not see URL equals evil.com, we would see destination equals some hash of the domain, and then, or some unique mapping, and therefore the application then converts that value back to the actual domain. So that would make it much harder for the attacker to construct their own URL pointing to their own website. So there are different ways to try and reduce the impact of these redirection attacks. Maybe the simplest is not to use these features. Just going back to what was the redirection. This is our node 4. This is our web server, our normal web server. What does the redirect page do? It was very simple. It includes some header. It's just some PHP. The main point is that this page gets in the URL the parameter. It extracts it from the URL and sets it to this PHP parameter called URL. And this header location is just some PHP code to do the redirection. So all it did was, whatever the value of URL was, for example, actually the examples here, whatever the value of URL is in the actual URL, then that PHP code redirects you to that value. So that's how it was implemented. Of course, it can be more complex than that. It's just a simple demonstration. Let's look at some other attacks. That was number 10. Let's go back and see others that... We've mentioned briefly sensitive data exposure. We won't say much more about that. So number 6 on the list. For example, if someone can steal the cookie values, then they can log in as someone else. Okay. We saw that last lecture, that the cookie, for example, contains the session identifier, something that identifies the user. If someone else can obtain those values, then they can set them in their browser to log in. So that is considered sensitive data, therefore we should protect it. So if HTTPS is not used, if we don't have encryption, then it's possible for someone to intercept those cookies sent between the browser and the server and steal those values, allowing them to log in as someone else. But there's many aspects of sensitive data that we should protect on websites. So not just cookies. When someone logs in with their username and password, you type in your username and password, press submit, it sends that username and password to the server. If that's not encrypted, then someone can intercept and see the username and password. Not just the communications, but also on the server itself. If the passwords are not stored properly on the server, then someone may be able to perform an attack and steal those passwords. So we've covered an entire topic on storage of passwords. It applies not just to operating systems, but to websites as well. That passwords should be, when they're stored, you don't store the actual password, you store a salted hash of the password. That is, you take the password, attach some random value, and take a hash of that and store the hash value. So that even if someone can perform some attack to download this list of passwords, they don't get the actual passwords, they just get hash values. And with a strong hash function, it takes too long to be able to go backwards from the hash value to get the password. So this is following the principles that we introduced in our earlier lectures. If it's not stored like that, then it's potentially exposing sensitive information to others. And other confidential information, say credit card numbers, that should be stored in a manner such that if someone performs some attack, that they still can't get access to that confidential information. We'll see what shortly an SQL injection attack. So, how do you prevent exposing sensitive data? Encrypt it. At rest and in transit means at rest when it's stored. For example, if the information is stored in a database, one option is to encrypt it before it's stored. Now, there are some issues with that, but so that's like with passwords. Or it's not encrypted, but hash the value. Don't store the actual value. And in transit, that is the communications between browser and server. Encrypt those communications. Don't store sensitive data that's not needed. So someone supplies their credit card to buy something, don't store it after they've purchased the item. Okay? That is, make that transaction and all right, check the credit card then, but don't, after it's all been finished, that transaction, don't store the credit card any longer. Which would mean that the user has to supply their credit card information again if they want to buy something later. So that's inconvenient for the user, but it means if someone attacks your website and gets access to the database, they cannot find everyone's credit card numbers. So there's a trade-off that needs to be considered. So one way to make sure that you don't expose sensitive data is not to store it, or store as a minimal amount as possible, as minimal amount as needed. Now, there's no one answer there as to what to store, but depending upon your application. All right, we know about storing passwords. Other ways, other things, for example, when forms, the web page is collecting private information, disable autocomplete. So not autocomplete from the browser's perspective, but some websites, you type in the first letter and the website actually sends that letter to the server, and the server sends back a list of possible strings that will autocomplete. So you type in the first 3 letters and the website sends back, okay, the words that start with those first 3 letters. So that makes it easier for the user, but that potentially exposes private information, because if an attacker can type in the first 3 letters and guess them, then the website would send back all combinations that start with those 3 letters that are already in the database. So using autocomplete on websites is a problem in some cases. We will not go into any more detail about, or give more details about sensitive data exposure. What else have we seen? Let's go back to the first attack, and the most ranked number 1 in this list of the risks for websites, injection. And let's do it on our website. Bring up. So we have our browser, and remember the feature is that students can log in. We have 2 students in this demo. They can log in and see their own grades. They cannot change their grades. And faculty members can log in and see everyone's grades and can change grades. Okay? That's the requirements. So let's just check and log in as a student. Now, here's an autocomplete. But when I said autocomplete before, this is the autocomplete of the browser. Okay? So browsers, when you type something in, may remember information from forms. And that's to do with the browser. But some websites, if you type in the first 2 letters here, those or characters, they're actually sent to the server as you're typing them in, and the website sends back a list here, and it's using JavaScript, sends back a list of potential values. When you search Google, it does that. You type in the first few letters on the Google website, and it sends back the potential list of the most common strings that match that. That's the autocomplete that I was talking about. Part of the server, not part of the web browser. We log in as a student. And just check, okay, this student, this ID can see their grades. Okay, so this student has grades for 2 different courses. They can view their grades. How can they view someone else's grades? Well, let's try. Let's go back to this form. This form of viewing grades actually takes a student ID. So this student, we're logged in as this student with all zeros, 5 all zeros, but they know that there's another student. Let's logged in as the student with all zeros, try and view someone else's grades. And no, the website checks. It compares, it's implemented such that the student that's logged in, their ID, is checked against who they're trying to view the grades for. If they don't match, and it gives this message saying you can only view your own grades. So that's just a simple check to say, compare who's logged in versus whose grades we want to see. If they don't match, you cannot view them. How does it know? How does the web server know who's logged in? From last week or last lecture, how does the server know who's logged in? The ID of the user. The session ID and the cookie. Okay, every time we send a request, the browser is sending a cookie to the server and including some information about that session. And we can see it here. This is the cookie for this domain, myuni.edu. There's a username and a hash. And the username for this cookie is this 5 all zeros ID. So this is the user that's logged in at the moment. So when we send a request to the web server, this cookie is included. And the web server knows about, okay, this is the user logged in, and they compare the logged in user ID against the ID of the student that we're trying to view the grades for. If they don't match, it returns an error. So we can't see the grades of other students. Let's try an injection attack. And an injection attack is about sending data to the server that triggers the server to do something it wasn't supposed to do. We inject data into the server so that it will do something malicious, preferably, from the attacker's point of view. So let's see one. So we're logged in as this student, all zeros. Let's try and see if we can see data of other students. And if we enter the course code, and I've done it before, so we've got autocomplete here. What I'm going to do, and this is the injection attack, I'm going to enter the course code, which normally means that the grade just for that course is displayed. But I've entered this strange string here, ITS 335, and then the single quote, or 1 equals 1. We'll come back to that. But I enter that in, and I submit. What happened? Let's go back. Made a mistake. This one. Student ID is the logged in user, all zeros, but I've created this special string here in the course code. And now the logged in user, all zeros, can see everyone's grades. So there are only 2 users in this database. They can see the grades of the other user. So this is an example of an injection attack where the the user has submitted data to the server that caused the server to do something unexpected. In this case, and it's very common, it's caused the server to display unauthorized information to this user, in particular grades of other users. And this is a specific and a very common called an SQL injection, because it took advantage of the fact that this website was using a database, using SQL to communicate between the engine and a database, and it took advantage of one of the limitations in the construction of the query. So let's see how that worked, what happened. To do so, we need to look at the code for what happens when we normally submit information here. So normally when we submit the student ID from this query page, query.php, we submit an ID and a course code. What normally happens is that the PHP code takes the information in the form and creates an SQL query to send to the database. The database then returns the information related to that query, and it's displayed on this page. So let's look at the PHP and the query on the server. It's in the view.php. And without having to understand all of the code, there's a few things that are of interest. Okay, this is just a check based upon using the session information, whether the user's logged in. Then this code, the view.php, reads the parameters from the post. So when you have a form and you click on submit, that sends a post request to the server. And the parameters of that post are the values of the form that you filled in. So we had a student ID and a course code. They were the two parameters. They were submitted to the server. And this is just the code for the PHP to extract those values from the post. So the ID is put into the variable ID. And a little bit later, the course code is stored in the variable course. So whatever we enter in the form, go back, whatever we enter in this field and this field will eventually be stored as ID and course in the PHP code. And then the PHP code, there's some just checking, we'll go down to the main part. It creates a query. It's hard to see. There's a check. It's hard to see. This is checking about the cookie to check, is the user either the faculty member, Steve, so the faculty member can do anything, or this last one, is the username of the cookie, scroll along, equal to the ID. So this was the check. Does the logged in user ID match the ID that we're searching for? If so, we can display the grades. So if we're logged in as this all zeros user and we're searching for the grades for this all zeros user, then we'll display the grades. One of these lines creates a query. So just an SQL query saying select star from course grades, that's the name of the table. Select everything where the student ID equals the ID in that field of the form. And actually I can just wrap that around, it'll be easier. Just temporarily. So where are we? Select star from course grades where the student ID equals ID, and then some ordering, that is, sort them by this order. This is if there is no course. So if there's no course field entered, then it shows for all courses. If there is a course, then it selects star from course grades where the student ID equals ID, $ID, and course code equals the value of course. Order by student ID. Student ID is the column in the database, and course code is the column in the database. So that's the normal query. Let's just summarize that one. I'll just copy and paste that to another file so we can see it. So that's our query that's executed. Now, in the normal case, when we enter in a course code here, go back, show you again. So the value of ID will be 5 all zeros, and the value of the course code will be ITS 335. So ID would be and course ITS 335. Therefore, the actual query constructed is, I think you'll know, we replace this ID with the value, and we replace $course with the value there. So that's the normal case, where when we enter in those values in the form, it constructs this SQL query, and that query is sent to the database. Select all values from course grades where the student ID is the all zeros and the course code is ITS 335, and it sorts them and returns them in the results, and it's showed on the web page. And it shows simply the ID, course code, and grade. Now, in the attack, look what I entered in the attack. In the course code, I enter ITS 335 and then the quote, or 1 equals 1. So let's put that into our query here. The ID is the same, but the course value is ITS 335, quote, or 1 equals 1. That was the value entered in on the form. And let's now see what it constructs in terms of the SQL query. We replace those values, the ID is the same, but here we're replacing $course with this string. And we end up with ITS 335, single quote, or 1 equals 1, and the closing quote. So the PHP, all it did is took this value and replaced $course with that value to construct the SQL query. What does this SQL query do? Can you remember how the queries work? With SQL queries, you know, okay, this is what we select, this is the table we select from, and these are the conditions. So the conditions are student ID equals 5 all zeros, and course code equals ITS 335, or 1 equals 1. When does 1 equal 1? Always. So what's true? This will be true. This condition will be true always. And because it's or, we have this value and this or this, which means this whole condition always returns true. Because if the student ID is, if this condition was false and this condition was false, still this returns true. So false or true returns true. So the result is that this query will always return all values in the database, all fields. And as a result, it's effectively the same as a query select star from course grades, order by student ID. Because we have this or true, everything's going to return true. So it means select all rows from the table. And star means all columns. And that's why we get this result. It submits the query and the result returned is all rows from the database. And as a result, the user with all zeros has now seen the grades of the other user. And if there are many users in the database, they would see the grades of every user. And this is an injection or an SQL injection attack. The most common or considered the number one risk in web applications. This one takes advantage of the fact that we're using an SQL query to extract data from a database, and that query was not constructed correctly. It allowed the user to construct a query that was doing something unexpected, in this case showing all data from the database. And now we've exposed sensitive information from that query. Any questions on how to construct, how to perform an SQL injection? Don't be confused by the name. SQL injection doesn't necessarily mean injecting data into a database. Okay? In this case, we're not sending any new data into the database. All we're doing is selecting data from the database, viewing data from the database. What we're doing is we're injecting data to the server, this data, such that the server does something unexpected. Okay? So we've sent these two fields are sent from the browser to the server, and the server is programmed such that when it receives this, it will construct an SQL query that will return everything from the database. How do you stop that? How do you prevent such an attack? Sorry? Detect what? Detect, okay. Don't allow the user to submit this value to the database. That's one way. So detect if the user submits this string as the course code, well, that shouldn't be possible. If it's a course code, it shouldn't have all 1 equals 1 in it. It should be just a 6-letter or a 5-letter character. So we could do some validation of the input. So validate the input that the user has submitted to the server. An ID, for example, should always be this, 10 digits value. It shouldn't be some other longer value or shorter value. It shouldn't contain letters. If we're using SIT as an example, the ID should always be 10 digits long. So if it's not, don't accept this query. That's called input validation. Validate the input that's submitted by the browser, by the user. Similar with the course code. The course code should always be, for example, 5 characters where the first 3 are letters and the last three are numbers. You could be even more specific, and let's say that we know all of the course codes in SIT. Then when a course code is selected here, an input, then we can compare it against the known ones. If it's a known one, okay. If it's something else, don't trust it. Don't execute the query. So input validation is one way. Because if you don't validate the input, then it allows the attacker to submit anything to your database. And if your queries are constructed in such a way, like in our example, then they can potentially do something unauthorized, in this case, view data. So this specific attack took advantage of the fact that the query, the general query in the PHP is this top two lines, took advantage of the fact that all we do is whatever was in the course field in the form is put here into the SQL query. So by programming the PHP better, we could have avoided that. So input validation is one way. Check what is the value of $course. Don't immediately insert it in there. Any questions about how to do that SQL injection? This one, again, is not injecting data into the database. It's injecting data into the server to get the server to do something unexpected. This is not modifying data, but other injection attacks can do things like modify data in the database. You can construct SQL queries that do much more advanced things. Depending upon the database server and the actual query format, you can construct things that insert data, that delete data from the database. So in some servers, it will allow you to combine queries so that, okay, you have select star from this, and then you have a second query at the end, drop star from this table. That is, delete everything from the database. Therefore, the attacker could delete data from the database. So back to our slides. The examples, which is similar to what we saw in our case. The application normally creates a query from some form inputs. So whatever the values are in the form, creates a query. The attacker enters a value into the form that causes some unintended query to be processed. So in our case, the course we'd expect to be just ITS 335, but the attacker created this special queries, this special string, such that the query becomes something that returns true in terms of the conditions, which means it selects all rows from the database or from the table. The result, in this case, the grades of all users are selected and therefore displayed. How do we stop it? Well, instead of creating the query direct, like I did in the PHP, instead of including this direct query, many processing languages, PHP and others, will have parameterized queries. We can construct a query in advance, and it will only allow a certain set of parameters to be passed into that query. It depends upon the database and the processing language of how that's performed. That's the recommended approach. So things like prepared statements and stored procedures are related to different databases. They can be used so that such attacks are not possible. Whitelisting or input validation. When there's some input from some untrusted source, so with respect to the server, anything that the user submits can be considered untrusted. Therefore, validate it. Check if this input is appropriate or not. So you can have a whitelist that says that The only possible course codes are these 50 course codes for SIT. If it's something else, don't allow it. Or escape special characters. So in this attack, the special characters were the single quotes and the equals in here. They shouldn't be allowed in the input form. So you can escape them such that the PHP would not process them as a single quote and an equal sign. That is, the query would have ended up like, and I can't remember the syntax, if we didn't allow those single quotes, it would have ended up like this, which is course code. The course code, this is the string that it compares against, ITS 335 or 1 equals 1. So when the database executes this query, it checks in the course code column, is there a value that matches this string? And it will return no, and therefore this would return false, this condition. So if we didn't allow the single quotes in this field, or if we extracted them from what was inputted, then the attack would not be successful. It's the fact that we allowed those single quotes and allowed us to construct a query that took advantage of that. So injection, and it's not just for SQL injection, there are many other forms of injection. Submitting data to the server that causes the server to do something unauthorized is considered the highest priority risk in web applications. Ways to deal with it, really the best ways is to program create a website correctly. And again, we will not go through it, but the OWASP website includes many guidelines of preventing such attacks. So they have what they call cheat sheets on many different issues, like parameterizing queries so that SQL injection attacks are not possible. So they have, maybe I won't try and load it. But if you want to create your website and you're doing processing of database from forms, then they have many different cheat sheets to show for different languages, PHP, Java, ASP and so on, how to program them so that SQL injection attacks are not possible. So query parameterization is one, and I think they may have a few others as well regarding SQL injection prevention, how to prevent them. Questions about injection? Broken authentication and session management. Well, we've seen a simple example of that if someone can steal the cookie, then they can log in as that user. Well, what if you don't use a cookie? Some websites use, so the cookie stores something about the session. Yeah. Whether the user logged in or not. Some websites don't use a cookie but instead store that information in the URL. That's worse. So including information about the session in the URL is worse than including in the cookie, because then someone just needs to capture that URL, find that URL, and now that they can steal this session identifier and use it in their browser, allowing them to access that particular session. So if session IDs are included in the URL and someone makes that URL available to someone else, then that receiving person can log in. Therefore, include session IDs in cookies only. It makes it much harder for someone to discover what those values are. Even better, encrypt the HTTP communications using HTTPS. What else? So other issues, okay, you log in. After some time, the system automatically logs you out, deleting the cookie. But if that timeout is too long, that is, the cookie is saved on the computer too long, then it means that if you leave the computer unattended, someone can walk up there and still use your session. Okay, so you do the quiz in Moodle in the lab and on one computer, and you finish the quiz, but you stay logged in and you leave, and then someone else walks up to that computer and they can do anything logged in as you on that system. So how do we stop that? The user should log out, but if they don't log out, we have a timeout. Say, okay, after 5 minutes, they automatically logged out. But if we make that timeout too long, then it gives a chance at an attacker to get access. If we make the timeout too short, it means if you just stop using a website for a few minutes, then you're automatically logged out and it's very inconvenient. Other aspects of broken authentication, okay, if someone can get access to the password database and discover the passwords, well, that's not good. That's a problem with your website. So use appropriate password storage and selection mechanisms. Let's go to another demo of, I think, number 8, cross-site request forgery. When I log in as a faculty member, I should be able to edit grades. So I log in. I can view the grades of other students. Okay, so I can view the grades of another student. They don't have to be my grades. It doesn't make sense for the faculty member. And I can click on these links to change the grades. So I can see that this student has a D+, a C, and an F for ITS 335. Okay. If I click on the link, I can change the grades. Let's say for ITS 323, and it's just a simple scheme where I can select the new grade to be, let's say, C+. And if we view again, ITS 323 has been changed to a C+. So this is a way for a user to modify data in the database. There's a SQL query that does an update on the database. How can a student change their grades? Well, let's look and see what the student could do. So I'm logged in at the moment. I can see this student's grades are D+, C+, and an F for ITS 335. I'm logged in, editing the grades, and then I receive an email. Let's bring up the email I just received while I'm editing. I just received an email while I'm editing from a student, and the student says, I found this nice website, okay, and all right, whatever the domain is. And I'm interested in free stuff, everyone is, so while I'm browsing, I'm bored with entering grades of students, so let's visit this website. And I think it's from a student that I don't know. I know this student. 5012345678, nice student, but getting an F for my course. I click on the link to the website. Nice website, it offers free stuff or whatever the website does. Okay, fine. Now I go back, better continue entering grades. Let's view the grades again. Just check. What's happened? This student now has an A for ITS 335. How did they do that? I didn't change it. I don't think you saw it was an F before. Then I visited some website and I come back to the grading system and now the grade is an A. Let's see what happened in that case. First, note, how is this changing of the grades implemented? So normally when I want to change grades, I select their URL and I can change by hovering over the link. It's hard to see, but there's an update grade.php, which takes 3 parameters in the URL: the ID, the course, and the new grade, F. Okay, that's the URL, and that submits the data to the web server, which then creates an SQL query that will update the grade in the database. So that's how it's implemented. So if I select F here, a query is sent to the server and the server changes the grade to an F. And go back and check again. All right, it's back to an F. Now, can a student send that query? So, could a student log in and try and update their grades? Let's try it. And I'll copy the link so people can see it. So, update grades. I'll copy the link. I'll log out and log in as this student. And now let's see if this student, it can... So that's the URL, but it's hard to see, but it takes 3 parameters: ID, course, and new grade. If we follow this link, what's going to happen? No, it's not that bad a website that allows students to change their own grades. So it checks. The student logged in is this 1, 2, 3, 4, 5, 6, 7, 8 student. They've tried to visit this link to upgrade their grade to an F, from an F to an A. But the website's implemented such that it checks who can update grades. The only person who can update grades is the faculty member. So because the server knows it's the student logged in, because the cookie belongs to this student who's logged in, and someone's trying to access this update grade code, and it's the student trying to access, that code checks. Can the student do this? And it's got a check that says no. Let's have a look. On the server, let's go to update grade. It has a check here that says if the username is Steve, then they can perform the code that updates the grade. But if the cookie belongs to someone else, like the student, then this would not pass and it returns an error saying you are not allowed to edit the grades. So the website's implemented good enough such that students cannot update grades. So how did it work? We still saw that the grade was changed from an F to an A. What happened? So we log out and try again. Log in. We were logged in as the faculty member. Who does the cookie belong to? It belongs to Steve at the moment. But then I was viewing the grades of other students. It's an F. Then I visited this other website, Free Stuff. Okay, because there was some email that I got saying, go to this nice website. So I went to this nice website, completely unrelated to the grading system. I visited and browsed through there. Let's just refresh. But let's just look at the source of this web page. The web page looks fine, all right? There's nothing malicious on here. But if we look at the source, there's the title, the header, some text, but there's an image in this web page. And the source of this image is in fact our MyUni website, and it has this link to update the grade of this student. And we'll scroll across. This student gets the new grade of A for this course, so that's the link. That means this image would be automatically loaded by the browser. Because what a browser does, when it has this HTML, it sees there's an image in here, therefore the browser visits this URL. The image width and height is set to 0. It's so that it's not displayed in the browser. So the user doesn't see any image there, but the browser actually visits this URL. The browser visits this URL, and remember who was logged in the browser. The user Steve was logged in. So the cookie that's sent to this URL is that is used for the user Steve. And we know that the website will allow user Steve to update the grade. And therefore the grade is actually updated. So there's several things happening there. So this is called a cross-site request forgery. We see there's this other site involved, this Free Stuff site. And we've sent a request from this other site. This Free Stuff website has sent a request to the MyUni website to update the grade. And because the user, Steve, was currently logged in on the browser on the MyUni website, the cookie for that was sent when this request was sent. Because what the browser will do is see, okay, a request is being sent to myuni.edu. Are there any cookies? Yes, there are. There's a cookie that identifies the username as Steve. So that cookie is sent in this request. Therefore, the server receives the request with the cookie showing that Steve is logged in and executes the grade update. So we've tricked the user into visiting some other website while they are logged in, and that other website has a link, a hidden link in this case, to the real website that does something that the student shouldn't be able to do, but the logged in user can do. The idea of including as an image, why? Well, because it triggers automatically the browser to visit this link. With browsers, what they do when they see an image tag, they actually visit this link to try and download the image and display it. There is no image here, but they'll still visit the link. The browser doesn't know. And what's shown is nothing because the image source, the image height and width is 0, so there's no image actually shown here. There's no problem. So the user that visits this website doesn't know that there was a link back to their grading system. And they'd only know that the grade's changed if they check later. Questions about how that attack works? Cross-site request forgery. Now, for this to work, the malicious user must have some control over this website. So they have this other website. Either they create their website themselves, or they use an existing website and put content on there that includes this image. Maybe it's a comment in a forum. So it's some content or some page here needs to have this image link to the real My Uni website. So a cross-site request forgery, CSRF. The application allowed the logged in user to change data. So Steve could change the data. The attacker has some other website that they control, and they include a link that's hidden from the user to make a change, and they somehow trick the victim, the person that's logged in, to visiting that link, therefore performing the change. Because the browser will automatically send the cookie to that domain if they're already logged in. So the victim, me in this case, was already logged in, so there was a cookie for this website, and when I follow this link, the cookie is sent, and therefore the server recognises it's me that's logged in, and therefore the update of the grade was changed. All right, these URLs on the slides are slightly different from our demo, but the same concept. So it requires the attacker to have some control of another website. It requires them to get me to visit that other website while I'm logged in. Okay. If that works, then we can perform some unintended action. How do we stop it? In every request that is sent includes some value that changes and cannot be predicted by the attacker. So even if the attacker could do this, the request that is sent in this case, when I click on the link, should be something that comes from the web server, so that the attacker cannot construct this link. If they try and visit this link, that they don't have this unique token, and therefore the server will recognize this is not from the actual user that's logged in. Make sure the token is in a cookie or a hidden field, for example. So hidden fields in forms can be used to include some token, some random value that identifies this is a request from the user that is logged in. It's not from someone who's creating this CSRF attack. So there are ways to do that. But if you just implement the updating, for example, in this simple way, then the attack's successful. So cross-site request forgery, again, takes advantage of the attacker, tricks the user to visit some page that sends a request to the real website while that user is logged in. Any questions on this last demo? Let's go through in the last couple of minutes just the other attacks, not through demos, just these slides. That was number 8. We've seen number 10 before, the redirection. Number 9, using components with known vulnerabilities. So if you use some software on your website that has some bugs, then the attacker can take advantage of those bugs. That's the main point here. So using most large websites, that the people who implement them don't implement everything themselves. They use software from other projects, from other systems. For example, using other libraries, other application development frameworks, content management systems. If you use these other systems in your website, but these have bugs, then again, someone can try and attack your website. So it's important to be aware of all the components you're using in your website, and in particular the versions being used, and keep up to date as to any announcements on bugs in those components. And make sure you have a way to test these components. If you update them on a regular basis, make sure that they still work. Let's go backwards then. Let's go back to the start. So number 1, injection, we've seen. Number 2, we've seen that is if the authentication is not implemented correctly, or the session management, then the attacks can occur. Number 3, cross-site scripting. Let's say there's a web page that's constructed using some unvalidated input. So some PHP that displays the value of the name parameter in the URL. Then that allows an attacker to create a URL that sets the value of name to some script. Okay, so here, http sit.th view.php name equals Steve. That may be the normal value, but if the attacker can submit anything here as the name, like Steve followed by script and some JavaScript, then what happens when they submit this is that this PHP executes or puts this script inside the page. So this JavaScript would now be put inside the HTML page, and when the HTML page is loaded in your browser, the browser executes this JavaScript. So inside the script tags is JavaScript. What does this script do? It redirects you to some evil website. Okay? To do different things. It may redirect you to some other website under the control of the attacker, which has some code that steals your cookie, that takes a copy of the cookie that was sent in the request, and therefore that evil website then has your cookie value and now can use that cookie to do other attacks, to steal your session. So this is cross-site scripting, using another website and using a script to redirect you to that other website, and does whatever it can do then. Steal cookies, just redirect you to sites that have viruses and so on. Again, this is about, there's some input, in this case in the URL, that is not validated. So how do you fix that? Everything that is submitted to your server, check whether it's trustworthy or not. So input validation. If name is input, then check that it doesn't contain any characters that are unexpected. So in this case, name, the string, it starts from Steve and ends all the way here. So escape untrusted data would be to, if this is a string, don't allow less than and greater than signs. Escape them. That is, effectively remove them from the string so that your browser would not execute this as a script. So remove all the untrusted characters in this case. Whitelist input validation. Again, if the input is this string, check it against a list of valid inputs. Is it valid? If so, it's okay. If not, don't process this. Return an error. So whitelist means check it against known good values. And there are libraries that will, so web development libraries that will help you do this input validation to escape characters and check data. So sanitize the input. The others we'll go through and finish next week. Okay, so the 2 or 3 that we haven't gone through, we'll just discuss them. We won't have any demos, but some are quite simple. We'll finish with them next week.